pleasure to be here. I like to keep things informal. We have a relatively small group here. You should be able to hear me, I hope. So if you have questions as we go, feel free to just ask away, and let's have some discussion going on. We can keep it as light as the topic deserves to be. So let me start with a comic. Here's a boy who's getting ready to go to school in the morning. He's talking to his mom, and for those of you who may not be able to read this, he says, "Yes, of course I've done my homework, Mom, but I don't need to carry it to school. It's on the cloud." Okay, we've probably all been there where we've had these issues about our kids doing their homework, and what's I find interesting about this comic is not that the little boy knows how to use the cloud. I mean, little kids are really good about adopting modern technologies and using them. What amazes me is that he's willing to trust his precious homework to the cloud, to some third party that he has no control over. Is that trust misguided? Probably not, actually, in this case, because if you go and you store your data in the cloud these days, these cloud providers do a very good job of taking that data. They replicate it for availability, so there's a really good chance that you're going to be able to get that data back. This little boy's homework is probably replicated on at least 3 servers in different failure domains, maybe 6 or 9 or more. Okay? But what this little boy probably doesn't realize is that when he gets to school and his teacher pulls up his homework from the cloud, she may get some older version of his homework. She may not get the latest version that the boy wrote. She may get a version that's only partially completed. She may get a version that he found errors in and later corrected. And that's because a lot of these cloud storage providers don't guarantee to give you the latest version of the data back when you do a read. They provide something called eventual consistency. So that's the nature of this talk. Okay, so what happens in the cloud today? You take your data. These cloud providers provide APIs that allow you to read and write data. They'll store it for you for indefinitely for a moderate price, pretty cheap these days. My bill from Azure was 92 cents last month. And I have a fair amount of data. So what happens is typically this data is written to a primary. So I'm going to describe how Windows Azure works, but these other storage providers are very similar architecture. So in Windows Azure, when you write data, it goes to a primary site. There are also 2 secondaries of that data, and these are all within one data center. Windows Azure also does what's known as geo-replication, which is they'll take this data optionally, but that's the default, and they'll replicate it across a different data center that's several hundred miles or a few hundred miles away, typically. And they have 3 replicas in that remote data center, too. So by default, you get 6 replicas, 2 different data centers. You can lose a complete data center. Your data is still available. What happens when you do a write? The writes all go to the primary, and then they propagate to all the secondaries within that data center before the user is informed that that write has completed. So that write is fairly durable. It can survive the failure of any of those machines. It's not durable across data centers, though, because what happens is this write gets queued up for a lazy replication, and eventually that data then that's queued up gets to the remote data center where it propagates. That's why it's known as eventual consistency, because at any point in time, all of the replicas of the data are not up to date. There are these geo-replicas that are typically inconsistent, and they are lagging behind the primary site by some amount. And it depends on how frequently these replicate. Okay, so what happens when you do a read operation? If you do a read operation and you go to the primary site, then clearly you get the latest value because it has the latest value. But some of these systems allow you to do read from arbitrary sites. So you happen to read from the secondary site, you may or may not get the latest value because it's, like I said, it's eventually consistent, and this is called an eventually consistent read. Okay, there's no guarantees about what value you get other than it's some value that was written at some point in time. Okay, so that's how, like I said, a lot of these systems work: Azure, Google, Amazon. Yeah, question?
A question about Azure. Does Azure basically have the equivalent of sync? That is, can you say update it now?
Can you say update it now across data centers?
Correct.
No. You have no control over the period by which Azure takes to replicate your data across data centers.
Does it have the equivalent of a probe instruction? Does it allow you to say, well, are they all in sync now?
As of 2 months ago, they do.
Ah.
Well, or you can't. You can say when is the last time they sync, and they will tell you the timestamp of the secondary. So you can use that to tell if it's sufficiently close.
So you don't know that all 6 sites are actually in sync.
And you can never know that because by the time the answer came back, the primary may have taken additional updates.
No. So I'm assuming like I wrote something down, and what I want to know is I want to be able to send a signal back to the user which says it's all safe, all 6 sites are now up to date. Is there a way for me to know for sure that all 6 sites are now good?
No, because like I said, they may not always be up to date because you can never guarantee that they're up to date because the primary continues to take updates. But if you have a particular update that you know was done at a particular time, you can go and ask them, is the secondary up to date as of this time? And it will say yes or no.
Okay, so I have a little bit of a syntax problem. All I wanted to say as the application,
Right.
I can say I closed down at this time.
Correct.
And when I start up again, I can say I logged my close down time. All 6 sites are now up to date.
You can say what was the last time that the secondary did a sync, and if that timestamp is greater than when you closed down, then you know it's up to date regard to the state that your application had. Yes.
Cool.
Does that make sense?
Yeah.
Okay. Okay. So what we're going to do today, I'm going to try to answer 3 questions. One is tell you about what consistency choices do systems provide today. 2, what consistency choices should they provide, and why? And 3, why are these choices useful? Okay? Okay, so let's look at some popular systems today. Amazon S3 is the most popular and the first cloud storage system. They provide something called eventual consistency, and that's the only guarantee they provide. You, as a user, don't have a choice. Most of the other systems today, even more recent ones from Amazon, like SimpleDB and DynamoDB, as well as Google App Engine, Yahoo and Peanuts and so on, provide a choice. So you as an application developer, when you go to one of these systems to do a read operation, you can say, for this particular read operation, I either want strongly consistent data, meaning I want the latest version of the data, or I'm willing to put up with eventually consistent data, meaning give me any version of the data. Even Windows Azure, which has been a very staunch supporter of strong consistency and has written papers about how important strong consistency is and so on, within the last couple of months, they've started allowing clients to perform eventually consistent reads. So in fact, Windows Azure also has the same 2 choices now. So this is pretty common now that you've got a choice. And the reason you have a choice is because there are fundamental trade-offs between consistency that you get and the performance that you get and the availability that you get. And we'll see a little bit about that in this talk. Okay. But if we look at the research community, these existing systems, as I said, are sort of on the endpoints of the consistency spectrum. They either give you strong consistency or eventual consistency. In the research community, we've been talking about consistency models for a really long time, right? 30 or more years, and there's all kinds of stuff that fall sort of in between, in the middle. Lots of stuff like, probabilistic quorums and session guarantees and epsilon serializability and fork join consistency and causal consistency, blah, 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 on and on and on. None of which is actually ever being used in practice. And I claim that the reason it's not being used in practice is because application developers don't really know how to deal with them. We haven't done a very good job as a research community of explaining them to people. And that's part of what I'm trying to remedy now by picking a few that I think are useful and that will make sense to application developers. And those are the few that I'm going to tell you about today. So here, if I could pick my favorite consistency guarantees, here are the 6 that I think make sense. We have strong and eventual consistency, or what people provide today. We have something that I call consistent prefix, meaning the order of all the writes that have been done to your particular data that you're sharing. A consistent prefix says that as an application reading the data item, you see an initial sequence of those writes. You may not see all of them, but you at least see the initial prefix of them. Monotonic freshness means that as an application reader, you will see an increasingly up-to-date version of the data. Okay, so if I show you a value of some data, I won't later then give you an older value. Read my writes means that you're guaranteed to at least see your own writes. Okay, so if you update the data and you turn around and do a read, you'll see the data that you wrote. There may be a later version that someone else wrote that you may or may not see, but you'll at least see the version that you wrote, or something later. And bounded staleness says that there's, some bound on how stale data I'll give you. That there's, when bound says, you'll see bounds can be different things, but for this talk, let's assume a bound is a time frame. So you can say, I want data that's at most 5 minutes out of date. Okay? So why did I pick these 6? Why are these the ones that I like? These are the ones that I believe that you can actually explain in a sentence to people and that application developers will understand. and that are not tied to a particular implementation. It's not about if the system does this and this and there's a failure here and the network partition there, then this is the consistency you get. Okay? So that's why I think we at least have some hope of making these useful to people, and what I'm going to do today is tell you why I think they're useful and what they mean. And so what I'm going to do now is explain in more detail what I mean by each of these, and I'm going to use, as the intro said, I'm going to use baseball as an example. I know what some of you are thinking. You're thinking, wait a minute, we're computer scientists. We know nothing about baseball. Okay? Don't worry about it. I will tell you what you need to know. I'm sure as computer scientists you can read code. So here's everything you need to know about baseball in an algorithmic form. Okay? So baseball has 9 innings. There's a home team and a visiting team. The visiting team bats first until they make 3 outs. Every time they cross home plate, they score 1 run. And then the home team bats until they make 3 outs, and this goes on for 9 innings. That's all you need to know for the purposes of this talk. Okay? So basically what happens, the most important part, is we have 2 scores that we have to maintain, one for the home team, one for the visiting team. Let's assume for this talk that this score is stored in a key value store in one of these cloud service providers. And now we're going to look at what sort of consistency do you get from that cloud storage provider. And what kind of consistency do you want in order to maintain this very simple data structure of 2 numbers, which is your baseball score for the current game that's ongoing. Make sense? Okay. So what I'm going to do is I'm going to go through, first of all, and explain the different consistencies. And so let's start with strong consistency. And for all of these consistencies, what I'm going to do is I'm going to start with a write log on the left here. That's the log of update operations that have been done so far in the baseball game. So in this particular game, the home team scored first, and so we wrote 1 for the home team score to our key value store, then the visiting team score, and we wrote 1 for its score, and then the home team scored a couple more times, and so we wrote 2 and 3. The visiting team scored again, so we wrote 2, and the home team scored 2 more times, so we did updates 4 and 5. Okay, so think of this as a write log from top to bottom, set of operations that have been done, write operations that have been done in the system, and now the question is, if I come along and I do a read operation, given that this write log has already taken place, if I do a read operation with a particular consistency guarantee, what am I guaranteed to see as a result of that read operation? For strong consistency, so clearly the current score is visitors to home team 5, right? Okay, if you offer strong consistency, then when a reader comes along, he's guaranteed to see the effects of all of these 7 updates, which for this particular example, really the last update to each score is the only one that really matters. But in general, I write these definitions in terms of the set of updates that are visible to a user, because in some cases, depending on your update model, the whole set may be useful, or may be important. So for instance, think of a bank account. If you have a bank account with withdrawal and deposits, then it's the set of withdrawal and deposits that determines the final bank balance. It's not the last withdrawal or deposit. Okay, so in general, we like to think about what is the set of write operations that's visible to a read operation. In this particular case, all 7 write operations are visible to the read operation, and that's true no matter who the reader is. Any reader who comes in and says, I want strong consistency, will get the score of 2 to 5. Guaranteed. Okay? In this particular talk, I don't really have time to talk about how these guarantees are implemented, so I'm really going to talk about the semantics of them and their effect on the application. But I'll have a few notes off to the side about implementation details, like it's easy to implement strong consistency by either reading from a primary or doing some quorum-based schemes, doing some 2-phase commit when you do an update to update multiple sites and so on. We can ignore all that detail for now. And I'm also going to maintain a little report card in the bottom which says what are the consistency, performance, availability of these different consistency choices. So for strong consistency, it gets an A on my report card because it's a very good semantic. But it gets bad reports for performance and availability because these implementations invariably require either reading from a designated server like the primary, and if that primary goes down, your reads don't succeed at all. They basically block forever or they fail. Or it requires reading from a quorum of machines, in which case you have to go out and find a whole bunch of machines to read from. So the performance is not very good in general for strong consistency. So let's move on. So eventual consistency, again, same write log, same score. Now some reader comes along and says, give me a read, I want to read the score, and suppose he sees the first 2 writes and the 4th write, then he will get a score of visitors 1 and home team 3. That's a perfectly valid answer for eventual consistency. Some other reader comes along at the exact same time, and he may see the 1st, 3rd, and 5th update, and he'll see a score of 2 to 2. That's also a perfectly valid score for eventual consistency. That's what eventual consistency means, is that you see some subset of writes, but all bets are off in terms of no guarantees about what you're going to actually see. Okay, so it's clear that you're not getting the latest score necessarily, and in fact, different readers at the same time can get different scores. It's easy to implement, and it provides not so good consistency, but it provides really good performance, because essentially in any of the implementations of eventual consistency, you can read from any replica that's out there. And so you also get very good availability. You read from the latest replica, and if it's down, then you read from whatever one else you can find. Okay? So what about consistent prefix? The idea behind a consistent prefix is let's give the reader at least some notion of what the database that existed, or the state of the system that existed at some point in time at the primary site. So this is, if you're from the database world, there's something called snapshot isolation. You can think of this as letting the reader read from a snapshot of the data. It may be a stale snapshot, but at least it's a snapshot that existed at some point in time. So in particular, some reader might come around and he might see the first 3 updates, and he gets a score of 1 to 2. Some other reader might see the first 5 and gets a score of 2 to 3. Both of those are perfectly valid answers if you're asking for a prefix proper guarantee for your reads. Okay, it's not so hard to implement, and it provides sort of intermediate consistency, and it provides decent availability typically, especially if you have a property of your system where all the updates propagate from the primary out to the secondaries in order. Then by definition, all of those secondaries are prefix consistent because they're receiving updates in order, and therefore you can read from any of them and get a prefix. Okay, what about bounded staleness? Bounded staleness says that you see all the writes that are old, by some definition of old. Some people have defined old by how far they are back in the write log. Some people have defined old by how much they differ from the current value of the data, and so on. I define old in a very semantically meaningful way, I believe, which is time. What's the time bound? Do I want data that's at most 5 minutes old, and so on. And what that means is that you take some cut through your write log, and there's an old part of the log and there's a new part of the log, and the guarantee says that you're guaranteed to see all the writes in the old part of the log, and possibly some of the writes in the new part of the log. Okay, so if some reader comes along, he sees the first 4 writes, they're the ones in the old part of the log, he'll see a score of 1 to 3. Some other reader might come along at the same time, and he also might see write 6 in the log, because that's part of the guarantee. The guarantee just guarantees that you're guaranteed to see the old ones, and you may or may not see some new ones, so he might see a score of 1 to 4, and that's fine. It's not so hard to implement, though it does require some usually assumptions about clocks and stuff I won't get into. And it provides decent consistency, though it's hard to argue about the consistency, performance, availability characteristics of the scheme, because there's a parameter here we have, right, which is the bound, and it depends on how you set that bound, what sort of behavior you get from the underlying system. So in particular, if I set my time bound to be 0, saying I'm not willing to tolerate any staleness, then I get the same properties as strong consistency. And if I set my time bound to infinite, then I get the same properties as eventual consistency. But the nice thing is I can set it somewhere in between, and I get intermediary properties. And intermediary performance, availability, and so on. Make sense? Okay. Yeah, question?
Is this theoretical? Does this depend on all the readers having consistent time synchronization? In other words, how would the delay or latency of time update affect this boundary of what you define as code?
So you're asking an implementation question. It doesn't require anything about clock synchronization. You could do it with no clock synchronization whatsoever. The simplest way to do it, though, is to assume that there is some synchronization of clocks between servers, and you can do it by having the servers record, the secondary servers, for instance, record what's the last time that they did a sync with the primary, and as long as they did a sync with the primary recently enough, then less than the time bound, then you can read from them, and if they haven't, then you pessimistically say that you can't. That's the easiest implementation. And as I said, Azure already provides that information, for instance. Does that make sense? Yeah.
So my question is, you're talking about readers here. your algorithm, you have writers. They read the current score and then they include one of the scores.
Yes.
So if their reads are not consistent, then the writes that you have here would actually be incorrect.
I should have said that. So I'm assuming a write model where all of the writes are, the consistency doesn't apply to writes because all of the writes get done basically at a primary site. They get strictly ordered. They all get serialized if they're done in transactions, right? And so the write model is exactly the same as you would have with a centralized system. And that's basically how most of these systems work. Okay, it's only when you come to readers where the data you're trying to read from replicas that are lazily updated that these consistency matters. Is there another question? Okay. Oh, yeah, in the back.
Have there been any experiments with alternative writer models?
Absolutely. There are people who have developed systems, myself included, that are known as multi-master update models, where you allow updates to be done in multiple places, and then you, after the fact, synchronize those replicas together. You could do many of these consistency guarantees for a write model like that as well. Strong consistency is harder in a model like that because there's no authoritative copy for where the latest value is, right?
But none of these big systems are doing anything like that on a particular great size.
None of these commercially provided storage systems are doing any sort of multi-master updates at the moment. Yes.
Is there any available data on the kind of optimization of with a wide variety of applications where you tune the time over here on one side, and then you have the other constraint as your performance on the other end. So you can have a multi-objective kind of optimization where you find different kinds of time bounds for different kinds of applications.
Correct. And I don't know of anyone who has actually studied that. Yeah.
So has anybody ever expanded your report card to include net energy consumption per transaction?
Not that I'm aware of. I think it would be an interesting thing to do. I haven't done it, and I don't know of any work that's done that.
Okay.
What did I just knock? Oh, I knocked over here. Oh, sorry. So you still know you're here. Okay. So monotonic freshness. Again, the idea here is that we want to provide an increasingly up-to-date view of the system to readers. Okay, so that means that if some reader comes along, like reader 1 comes along at time t1, and he does a read and he sees update 1 and update 3, and he gets an answer of a score of 1 to 2. Now this same reader comes along at time t2, he's guaranteed to at least see update 1 and update 3. But he may see some additional ones as well. So in this particular case, he sees 1, 3, and 4, 1, 3, 4, and 5, and he gets a score of 2 to 3. And those are perfectly valid answers for monotonic freshness. So in other words, from a baseball score point of view, he sees a score that's increasing over time. Right? He'll never see a score that goes down. That's monotonic freshness. It's again, intermediate consistency, performance, it can be actually quite good because if you think about it, if you read from your nearby replica right off the bat, then you can continue reading from that replica, okay, because it's going to guarantee to be, assuming the replicas don't forget data, right? Once you start reading from someplace, you can continue to read from that place. So if you start reading from your local replica, you can continue there and get good performance. The only time you have to switch potentially is if that replica becomes unavailable, and then you have to find someone else to switch to that's at least as up to date as that one that you were reading from before. Okay, and the last one is read my writes. Very simple guarantee, very popular with developers. I don't know of any systems that provide it, however. And the idea here is straightforward. You know, if you do a write, turn around and do a read operation, you see what you wrote. So in this particular case, we got the same write log. If you're the scorekeeper and you've done all 7 of these writes and you do a read, then you're going to see a score of 2 to 5 because that's the guarantee. If you're some other reader in this particular case and you haven't done any writes whatsoever, then it looks to you like eventual consistency because you can get any subset of writes. If you've done some writes, then you'll guarantee to see those. So in this particular case, any other reader, if we assume that the scorekeeper is the only guy who ever does a write, then everybody else who's reading could see arbitrary scores. Okay, so those are the,
Is this a
yeah.
specific kind of eventual consistency? It looks like eventual consistency doesn't define some parameters, and this goes a little bit, defines a certain number, set of conditions, but
All of these define additional conditions on eventual consistency, if you think about it that way, right? So monotonic freshness requires additional guarantees that are of a timely nature, right? Bounded is an additional guarantee, and so on. So they're all basically, all of these intermediate consistencies are in some sense stronger than eventual consistency, right? They provide additional guarantees because they restrict the set of acceptable responses to your read requests.
here we're looking at a condition that considers multiple writers.
This condition only applies to you as a writer. So this is what's...
But if there are several people writing, would each one see a different kind of consistency?
They will see a consistency that applies to their rights, yes. So this is what's known as a session guarantee, meaning that there's a notion of begin session, I've done some writes, and now I've done a read, I'm guaranteed to see the writes in my session. If you have your own session, you've done some writes and reads, you'll see the writes in your session, but our two sessions are independent. There's no guarantees that I'll see your rights, and there's no guarantee that you'll see my rights. You may see my rights, but there's no guarantee about that.
But if there's conflicts between the rights?
If there are conflicts, so in our model, again, since we assume a primary update, there are no conflicts because all the updates are going to the primary and they're all serialized. If you have a multi-master, when you have to do conflicts, then conflict resolution has to happen somewhere, and there are well-known techniques for doing that, but that's orthogonal to any of these guarantees. Okay, so that's the 6 guarantees. There we go. So why is it that people are interested in different consistency guarantees? I think I already said that. And the reason, as we've seen, is that there are fundamental trade-offs between consistency, performance, and availability. Yes?
I wanted to comment. I noticed that of your additional 4, they're almost completely orthogonal to each other.
Correct.
You could have, it's almost like these are 4 flags, whether they are true or false. It's not so much that these are different models, these are just all different guarantees that may be present. You could have 2 or 0 of them and still be completely valid.
Very good observation. You can combine these together, and by combining them, you'll get a stronger guarantee. So in fact, we have a system that we've developed where you can specify any of these 4 that you want to put together in any combination. And as we'll see in the rest of this talk when I get to it, there are some examples of where, in fact, you want to do that. Yeah?
With monotonic reads, you have the availability as B there, but if you're writing to your primary and it goes down, then everybody's blocked, because if anybody was reading from the primary had recent information and everybody else has later information, so they can't see anything.
So if you were reading from the primary and the primary went down, then you are basically blocked. But most of the people are probably reading from their local replicas, and so the primary goes down, they can continue to read from their local replicas. And so that's why it's actually, in practice, pretty good availability. Yeah?
So in all of these systems, you are assuming there's, is it safe to assume that there is no client-side logic and no client-side caching of any kind?
No, so you can do client-side caching on top of this and so on, and then you have to think about how that affects your guarantees.
But most of your examples are assumed.
Right. So for all of the examples that I've talked about, I've been mentally assuming that there was no client-side caching and telling you what happens if there's no client-side caching. But for things like read my writes, if you cache all of your writes locally, then you can do reads locally, independent of what the replica state is, for instance. Okay, so what I'm going to do now is I'm going to, and by the way, you should take these ABCs and stuff with a big grain of salt, right? Because it depends a lot on your workloads, on your server configuration, on the implementation details, and so on. And in the case of like bounded consistency, on the bound parameter, and so on. But they're general guidelines about how these things compare, and there definitely are performance trade-offs, which I'll show you at the end of the talk. But what I'd like to do now is hopefully convince you that one of the reasons you want different guarantees is because it's this complex space of trade-offs. and we have to sort of allow developers to pick a point in that complex space of trade-offs that makes sense for their particular application. And what I'd like to do in the rest of this talk now is look at why and where these different consistency might be important to an application. And in order to do that, I'm going to go back and we're going to talk about baseball again. Same scenario, so don't worry about this slide again. And what I'm going to do is I'm going to run through some different participants in this baseball game that's ongoing, and I'm going to show you the snippets of code that they would run and what reads and writes they're doing on the system, and then we're going to have a discussion about what sort of consistency these different players want for their reads. Okay, so let's start with the official scorekeeper. Official scorekeeper is the guy who keeps the score. So let's suppose that the visiting team just scored a run. So this is the code that the official scorekeeper would run. He reads the visitor score from this key value store, he adds 1 to it, and he writes it back out. What consistency does he want for that read operation? Suppose you have a system that gives you these 6 choices of consistency. So let me remind you what the 6 are. Which of these consistency choices would you, as the application developer who wrote this piece of code, choose to use? Okay, I'm hearing strong. And I heard someone say read my rights. How many people vote for strong? No one's voting for strong. Oh, come on. Read my rights? Okay, someone explain to me read my rights.
Because he's the writer.
He's the writer. Okay. He definitely wants to receive the latest value when he does that read operation, right? Because if he doesn't get the latest value, when he adds 1 to it, he's going to write back an old value, and the visiting team's going to be really unhappy because they just got screwed out of some runs. Okay, so he definitely needs the latest value. But an important observation is he doesn't have to do a strongly consistent read to get that value, because we have certain semantics we know about this particular application that we might assume is that there's a single scorekeeper. If there's a single scorekeeper, then this is the only guy who does a write operation, so we know that that value he's reading is the value he wrote. He's the one who wrote it last time. And so read my rights, in fact, what did I just do? Oh, sorry, pushed the wrong button. So he wants strong consistency, but he in fact can get strong consistency with read my rights guarantee. It's an important observation. Does it matter in practice? You bet it might, okay? Because think about what happens in practice. Strong consistency says you go to the primary site and you read from the primary site. That primary site could be across the world. If this game is being played in China and the primary site is in Microsoft headquarters in Redmond, that's a 400 millisecond round trip time to do that read operation. Whereas if you do read my rights guarantee, what does that mean? It means you can read from any replica to which that write has already propagated. So, in a baseball game, it may be an hour between different scores, right? In an hour, that write has probably propagated all over the world, in which case you can do a local read. So in fact, performance-wise, this could be a couple orders of magnitude difference in performance just from that one change without giving up any semantics. Okay. Now we have the umpire. Okay, what does the umpire do in a baseball game? The umpire doesn't actually care about the score for most of the game. There's only one point in the game where he cares about the score, and that's when it's the middle of the 9th inning, and he has to decide whether the home team that's coming up to bat at the bottom of the 9th inning should bat or not. If the home team's already ahead, the game's over, they don't have to bat. So the umpire reads the visitor's score, he reads the home score. If the visitor's score is less than the home score, he ends the game. What consistency does he need? Can he do read my rights? No, because he never did any writes. He just sits back there and reads. Okay, and he only does this one read ever. So he needs strong consistency, and there's no option but to give him strong consistency. Okay, so he better, when he writes his program, say, I want a strongly consistent answer at this point in the code. Okay, what about the radio reporter? Okay, so if you live in the Bay Area, which I assume most of you do, and if you're like me, you listen to KCBS where they give you the sports score every half hour. So this is what the radio reporter does. He reads the visitor score, he reads the home score, he reports the score, and then it goes to sleep for 30 minutes and comes back and does it again in the next half hour, right? What kind of consistency does he need for these reads? Does he need strong consistency?
No. Increase it.
Do you expect the stuff you hear on the radio to be completely up to date? No, not really. Okay, so what are the options? Bounded,
He needs the prefix.
Prefix, okay. What else?
Monotonic.
Monotonic. Okay, so let's get some. So I like the prefix answer. So why do you think we need prefix?
You get scores that never really happened otherwise.
Exactly. So suppose what happened is the home team scored once and it scored twice. So the home team went up 2-0, and then the visiting team scored once. So now the current score is 2-1 in favor of the home team. He goes and he reads the visiting team score with an eventual consistency read. He gets a value of 1. He goes and reads the home score with an eventual consistency read. What value could he get? He could get anywhere between 0 and 2, right? He might get 1, and now he reports the score is tied 1-1. The game was never tied, right? That's just, bad reporting. Okay? So how do we prevent that? This is exactly what prefix does for us. Right? Prefix says we're guaranteed to see an initial prefix of the set of write operations. So prefix reads will give us a score that happened at some point in time. Right? Maybe not the latest score, but at least the score that happened at some point in time. So we definitely want a consistent prefix. Do we want anything else other than that?
Monotonic.
Why do we want monotonic?
Never goes forward.
Okay, we want monotonic so you don't report a score of 1-1 now, and then the next thing you report a score of 1-0, right? And so it looks like someone lost a run, which by the way doesn't happen in baseball. Okay. So in fact we want monotonic. Okay, again for those reasons. So here's an example, as the gentleman pointed out in the back, where you really want two consistency guarantees together. Okay, you'd like to be able to request both of these. Okay, does anyone still think we want bounded?
Yeah, we probably do.
Okay, we probably do. Why?
They guarantee something. They can't be 2 hours out of the day.
Can't be 2 hours out of the day. Okay.
It has to be within 30 minutes.
Okay, it has to be within 30 minutes. Okay, suppose I put a bound at 30 minutes. What would that mean?
You could have the same score twice.
Now, suppose I made it 29 minutes, okay? That would mean that my score is at most 29 minutes old, right? Do I still need monotonic freshness in that case?
Yes.
No, in fact. If you think about it, if I have a bound, if I only read every 30 minutes and I have a bound of less than 30 minutes, that guarantees me monotonicity. So in fact, you could use bounded inconsistency or bounded staleness in some cases to get the same effect of monotonicity. So I could in fact use monotonic freshness, or I could use bounded staleness to get the property that I want there. So if I do really want to have scores that are at least not too old, like maybe 15 minutes old or something, then I might as well just use bounded staleness and forego the monotonicity. Make sense? Okay. Let's move on. There's a subtlety that none of you picked up on that sometimes people do, which is I said the consistent prefix was good enough. In fact, a consistent prefix is not good enough the way I wrote this code, because if I do a consistent prefix of the visitor score and then I do a consistent prefix of the home score, it doesn't really mean anything. Okay, because the consistent prefix of one set of values and a consistent prefix of a different set of values is just any value from that set, right? In this particular case. So in fact, what I want is I want a consistent prefix applied to the snapshot that's read by both of those read operations together. So in fact, I want to do is I want to take those two read operations, put them in a transaction, and get a consistent prefix on the snapshot read by that transaction. It's a subtle point, but I thought I should point it out. Okay, here's the sports writer. I used to be a sports writer, so I know how this works. So I was a sports writer when I was in high school, so I didn't do too much of this. But basically, they hang around during the game, don't do anything. At the end of the game, they decide to go out to dinner with their buddies, usually the other fellow sports writers, and then they come back an hour later to write their report, to write the article for the newspaper or for ESPN.com or for whatever today. So what they do is they come back from dinner, they read the visitor score, they read the home score, and they write their article. Okay, what kind of consistency do they want for their reads?
If their dinner is longer than the eventual consistency update.
Okay, so if their dinner is longer than an eventual consistency update, they should be okay. So you might argue that they went out to dinner for an hour. Any system that doesn't propagate updates in an hour is not worth its salt. So they should just do an eventual consistency read and be done with it. If you were a sports writer, would you do that? I don't think I would, because the problem with that argument is there may be some replica that was down for that whole hour that you were gone, and just as you came back from dinner, that replica with stale data came up and got put back into service before it had a chance to synchronize, and now you happen to read from it. Okay, so you shouldn't make any assumption in practice about how long it takes for data to propagate. And so in fact, if you were the sports writer, you really want to get the up-to-date data, right? You want correct data. So how do you go about getting correct data? I heard someone say bounded. How does bounded help?
You know how long it takes between the end of the game and when you finally sit down to write the article, and that's how much time you sit.
Absolutely. If you know you were at dinner for an hour, you might as well do a bounded read of an hour and you'll be done with it, right? You're going to get good performance because chances are in that hour everybody propagated out, the data propagated out to everyone, and so your bounded read is going to return really quickly, and if there's some replica that happened to just come up, you're going to ignore it. So in fact, bounded staleness, I said, is the best way here to get strong consistency. And again, you get the benefits of strong consistency without paying the cost of it. Okay? So statistician, I got two more. Statistician waits for the end of the game. This is the guy who's keeping track of the stats for this team for the whole season. So let's assume this is the home team's statistician right now at the end of the game. He reads the home team score. He reads the number of runs they scored for the season thus far. He adds those runs to the score to those runs and writes it back out for the season stats. What consistency does he want for this read operation? Or for both of these read operations? Or for either of them?
Strong.
Does he need the latest value? Yeah, right? Okay, so he needs strongly consistent data. Does he need strong consistency? Well, he certainly needs strong consistency for the first one because he never wrote that value. The second value, we can make the same argument we made for the Scorekeeper, right? Where he's the only one who ever writes out the season stats, assuming there's one statistician. You're willing to make that assumption? Then we can use the read my writes by the same argument we had before for the second one. So here's an example of where within the same piece of code, the same program is running and it wants different consistency guarantees for two different read operations that are back-to-back in the code. Okay, so this argues that if you're providing a storage system for people, give them the option to specify not only on the program level, but at the individual read level what consistency they want. Okay, the last guy. This is a statwatcher. This is a guy who sits around with his buddies drinking beer and bragging about how many runs his team has scored for the season. He reads the season runs, he discusses it with his friends, and then he goes to sleep for the day and wakes up the next day and does the same thing. Okay, what kind of consistency does he need? You pick whatever you want. I argue eventual consistency is probably good enough for him because he doesn't care anyway. So he might as well be done with it. Okay, so those are the examples. Okay, so if we look at the summary here, couple of observations to make. One is all 6 of these consistency choices have appeared somewhere on this slide. Right? They've all been useful somewhere. In some cases, we've seen that we want to combine them together to provide the right guarantee. And as we said, you can combine any arbitrary subset of them together. It doesn't make sense, of course, to combine strong with anything else because it's already strong. And it doesn't make sense to combine eventual with anything else because they're already at least as good as eventual, but the other ones make sense to combine. In some cases, you might want to have different ones for different reads within the same program that I just said, and so on. And so if you're designing a storage system, I claim this tells you something about what you need to do to provide your API to the application developers. You need to give them these choices. I should point out that giving strong consistency as the only option would provide the correct semantics in all these cases, right? But it may not be the right thing for performance and availability, okay? So by doing strong consistency, you're giving up performance. And so the exercise here was, what's the minimum level of consistency that's tolerable to this program under the assumption that you're going to get better performance if you choose a relaxed consistency model. Okay, is that really true in practice? I just made these observations. I think I'm done with those. Is it really true in practice? I have one more slide that I want to show you with some actual numbers to show that, in fact, it's true. These are numbers that I collected 2 weeks ago at a TechFest event in Redmond. So the way I collected these numbers is we have a system that we've built here in Microsoft that's called Pileus, where we provide these 6 different consistency levels, and we allow you to pick them, to combine them in whatever way. We allow you to choose on a read-by-read basis what consistency you want. This is all built on top of Azure, so we can store your data in any Azure storage site throughout the world. We'll replicate it across any number of sites. For this particular example, the system, as I said, is Pileus. We have 4 replicas, one in a data center in West Europe, which is the primary site. I believe it's in Dublin, Ireland. We have one in North Europe, we have one in the west coast of the US, and we have the data replicated in the east coast of the US. I have a client running on my laptop here, sitting in the Executive Briefing Center in Redmond, and it's running something called the YCSB, the Yahoo Cloud Serving Benchmark. It's a set of read and write operations that it's doing, and the replicas are periodically syncing with each other. And now what we did is we run this benchmark. We selected different consistencies for each instance of the benchmark. I measured the round-trip performance of each read operation while running this benchmark with these different consistency choices, and here are the numbers I got in milliseconds. You'll see they range from 179 milliseconds to do a strong consistency read on average to 25 milliseconds to do an eventual consistency read. That's a factor of 7 in terms of performance. I should point out that if this application was running within the data center, within, let's say, the West Coast data center, then these numbers for eventual consistency would have been like a millisecond. And the number for strong consistency still would have been around 180 milliseconds. So in that case, it would have been 2 orders of magnitude difference in performance rather than a factor of 7. But even a factor of 7 is significant. It's enough that developers care about it. And the other observation is that if you choose intermediary consistencies, you in fact get intermediary performance on average. Okay, so this choice of consistency really does matter to application developers who care about performance. And so this exercise of trying to pick what's the minimum level of consistency we can give you that's tolerable for your application makes sense as long as application developers can understand the semantics that you're providing them and they presumably understand their applications and what it needs. Okay, so that's all I was going to say. What did I do? I have a conclusion slide, I know. So basically 3 takeaway points. One is all these cloud storage systems replicate data, and you want to provide consistency choices because there are fundamental trade-offs between consistency, availability, performance. Current systems allow you to choose between strong and eventual, and I'm arguing that in fact you want to provide intermediary consistency choices. Some things like read my write seem like no-brainers because they're easy to implement and they're cheap, and they provide a stronger consistency than eventual consistency. But it does put a burden on application developers, and so we have to be a little careful about how we present these to application developers so that they can, A, understand the implications of the consistency choice and deal with their application semantics. And the right choice of consistency, there's often not a single right choice, which is a problem, and that's some of the work I'm doing now is trying to figure out how to package this in a way that application developers can declaratively specify here's the tolerable consistency, here's the tolerable performance, and let the system underneath the covers do the right thing for them. And that's work I can tell you about in a different talk. But thank you.
Like consistency and optimization.
Correct. Questions? Any other questions? Yeah.
The eventual consistency really taking over the world, since a lot of things are statistical in nature, and if you lose data, it doesn't matter?
Eventual consistency. So that's an interesting question, right? So 20 years ago, when I first started building eventually consistent systems, all the database people beat the heck out of me. They said, oh, no one wants anything that's other than strong consistency because no one knows how to deal with it. And now, 5 years ago, basically all the systems we were building were eventual consistent, right? With a few exceptions. And eventual consistency has mostly taken over the world. Social networking sites are all eventually consistent. Data analytics, as you point out, are all eventually consistent and can deal with eventual consistency. There are still some sites where you might need strong consistency, which I also hope the message from here is that there are examples where you really do want strong consistency, right? But they're not universal. So one of the examples that I go around and I ask people, what do you want strong consistency for? The one application that I get 99.9% of the time. You know what it is? Banking. Everyone says you want strong consistency, but banking, which is total bull, because our banks are not strongly consistent, right? They do online recognition. They do offline bank recognition at night, right? They take all your checks, they process them at night. They're eventually consistent. They might be eventually consistent on a day-by-day basis, but they're eventually consistent. Yeah.
When you just said eventual consistency on a day-by-day basis, you added another condition. So it sounds like eventual consistency has a time interval or a temporal value you can attach to say how eventually consistent it is.
Correct. So we've already seen that in bounded inconsistency, right? I gave you a temporal notion, but there's another time notion which was hidden in all these guarantees, which is how often do these replicas synchronize with each other, right? And so if you do that, if you guarantee that they synchronize once a day, for instance, then you at least have a bound, even with eventual consistency, of at least of at most a day, right? Yeah.
So this is related to what you just said. If you have eventual consistency, you seem to want to get a status of when the eventual becomes yes, I'm consistent. And that's built into these systems that they all agree we're now all consistent.
No, that was just, if I understood you, that was the question I got at the very beginning of the talk, right? Which is, do these systems ever know that they're eventually that they're all consistent? And the answer is you can't, because unless you're willing to make assumptions that the primary is not accepting updates right now, the primary could be accepting updates that aren't being propagated out, right? And so in practice, these systems are never strongly mutually consistent, right?
The way the banking works, there's a cutoff time, consistent as of
Well, but even that's not true. If you go to your ATM, for instance, and you ask, "What's my current bank balance?" it may give you a different number than if you went to the bank's data center and asked it.
But the banks all give me a close of business, or I know my bank account today. I get a number which is my balance as a close of business.
As of now, close of business with assumptions about checks that are on hold and blah blah blah, right? Yeah.
Between a strong consistency and eventual consistency among the other four models you mentioned, do applications need to be aware of replicas?
Do applications need to be aware of replica? So the intention here is you shouldn't have to know where the data is replicated. You shouldn't have to know how many times it's replicated. You should just say, here's the consistency I want, and that's the semantic guarantee I want, independent of how the data is replicated. That's the idea. You shouldn't have to say, I'm reading from this particular replica, or I'm reading from that. That's too low level. We need to provide a higher level of abstraction, and that's what we're trying to do with these consistency guarantees. Yeah?
In your talk, you said the only time the umpire needed strong consistency was in the middle of the night.
Correct.
But doesn't he need it at the end of the game too?
Well, so if the umpire is the guy who's recording the official score, yeah, the scorekeeper is the guy who's officially recording the official score, then the umpire just cares that there are 3 outs at the end of the ninth and he's done.
No, because what if it's tied?
Oh, yeah, okay. Yeah. So he has to know whether it's tied. You're right. Okay, yes. I stand corrected.
I know baseball.
You're correct. You're correct. He has to know when he can end the game when it's not tied. Correct. If it has to go extra innings. Yes.
So I was wondering, has there been an evolution of data science and program science so that we can understand when slowly changing data? Because that's the essential model that you're using. Slowly changing data has slowly changing consequences, so that you can basically say, okay, I can relax my consistency constraints because I'm not running the nuclear power plant with this code.
Okay. Very good question. I think we need to get there. I don't think people are there. I think there's a lot of research, interesting research to be done there. Yeah.
Just one thing about the eventual consistency. If you're doing daily updates, you're not guaranteed a day because you're only a day out because one of your replicas could be down.
Correct. Exactly. That's why it's very hard to make any sort of, as I said earlier, any sort of guarantees about how stale you're going to get. Unless you, but you can do things like when you bring a replica up, you put it in write only mode until it's sufficiently caught up, right? Over here, yeah.
I'm not sure whether you just made that rhetorical question whether anybody needs strong consistency.
Did I say that? I don't think I said that.
Amazon used eventual consistency for some time, right?
Pardon me?
Amazon,
Yes?
and I think Werner Vogels actually invented that term.
Well, actually, I invented that term, but
You say that,
Werner stole it
I
from me.
personally have experienced that Amazon sent me an item twice, even though I ordered it on.
Yeah. So Amazon shopping carts, for instance, are perfectly eventual consistency. Yeah.
So Vogels himself had this famous tweet where he said he takes it back and he doesn't believe in eventual consistency anymore. So can you give a real world example where eventual consistency is enough?
I gave you several examples in this baseball example where you saw it's enough for some people and strong consistency is required in some cases.
Well, I mean,
you don't consider this a real world example.
Say photo sharing on the web or Evernote, or
So
like
eventually,
something that I as a user would actually use.
So as I said earlier, social networking applications are eventually consistent. People don't seem to mind that very much. Data analytics are eventually consistent as long as if you're doing some sort of aggregates over a large data set. The fact that you're missing some items from that data set doesn't really matter, right? Yeah.
Hi. So I was wondering, the implications of your talk is that a lot of operating system people are about to have their heads severely torqued because you're going to introduce a whole new mean into the file system paradigm, which means several people can open a file differently, and the operating system has to handle that.
Correct.
Right now, we have one inode, or we have one data structure that manages files, and when somebody does an F control, the guy who's the biggest asshole wins. And you're going to have to say that basically you have to have a per process model of what an F open or an F control means. So I was just wondering, how do the operating system people respond to your notion that they have to like rip everything apart?
I think it remains to be seen. I am an operating system person. I did present our system at the latest operating system conference, the big conference called SOSP, and they did accept my paper, so at least there's some positive reception. But how it's going to affect file systems and future operating systems, open-ended question. Unknown.
Okay.
Behind.
Well, you previously said that rights, a right is a right. Right, and the fiction rights is blocking you infer. So if you haven't changed your rights semantic, for the operating system, you perhaps change the reading.
Correct. So for everything I've said so far, and in our system, we don't change right semantics. We only affect read semantics. As I said, in response to another question, you could imagine different right semantics as well, but I haven't gone there. Yeah.
So as people are getting used to this eventual consistency, right? Can I say that what's more interesting is not about consistency or non-consistency. It is more about how soon the user can get the latest snapshots or performance, right? Is that what you think the people are more concerned with?
So how soon meaning, so I don't know, so by how soon do you mean how stale, or do you mean how soon in terms of performance?
Yeah, I mean how stale.
How stale.
Right.
So the interesting thing is these guarantees are not all about how stale, right?
It's not how stale. I think, for example, Facebook, right? And you receive the live, the feeds from your friends, right?
Right.
Right.
So Facebook is an interesting example.
And I think the measure is how soon.
So it's not all how soon. That's the point of these guarantees. And Facebook is an interesting example. I have friends at Facebook. I don't think I'm divulging any secrets. Facebook doesn't actually care about how soon you see someone's post. If someone posts something on your wall, they don't actually care about how soon you see. But what people get really upset about is when they post something and they turn around and their post doesn't show up immediately, right? So they want the read my rights guarantee, right? Okay, if I post something, I want that thing I posted to be on my page immediately, right, when I see it. I don't care if you posted something a day ago and I don't see it, right?
That's actually the same thing, actually. Imagine yourself being a different person, right? You're viewing yourself.
But it's not the same thing. So the point here is that the staleness of the data that people care about depends upon who wrote that data and the nature of the data. There's not a uniform model for staleness that people care about.
when you did your performance testing, did you do any hardware sensitivity analysis? Like, did you say, well, suppose instead of disk everything's flash, or instead of 10 gigabit, I now have 1 terabit networking? What happens to the results?
We didn't, and for the stuff I'm talking about here, the numbers I showed here, the performance is totally dominated by network latency, right? So the speed of your disk is irrelevant. If you're talking about it takes 400 milliseconds to get across the world, the speed of your flash versus disk doesn't really matter. The size of your database doesn't really matter that much. So we haven't worried about it.
Okay.
Okay, well, thank you very much.